Hello, future engineers. Welcome to my YouTube channel. If you're still new to my channel and you like what I'm doing, please don't forget to share my videos to your friends and to your friends' friends, to your younger brothers and sisters who would want to take up engineering in the future, and to your relatives. That's one way you can keep me going, inspired, and refreshed. Now, if you find my videos interesting and important to your studies, also please don't forget to subscribe.
Hello, students, subscribers, viewers, and future engineers. Here is another video in calculus, particularly on the application of slope of tangent to the curve, and this time the derivative which is interpreted, first derivative which is interpreted as the slope of the tangent to the curve may now be interpreted also as a rate of change, although in problem 3 it is an application of derivative as slope of tangent to the curve. Allow me to present the solution that is ready-made, not less animation, so that I can explain the solutions in just a short while. So here is the first problem. A body of gas is contained in a vessel of volume V. The pressure is given by the formula pressure equals constant over volume. Find the rate at which pressure increases with decreasing volume at the instant when the volume is equal to 4 units. So let's focus on problem 1 first. So this is the given formula. Pressure is inversely proportional to volume, and remember from gas law, when the temperature is held constant, PV equals constant. So that's why pressure is constant over volume. So the derivative of pressure with respect to volume is equal to, remember the guide formula, negative K over V square. And you may also rewrite this equation into K times V to the negative 1, so that the derivative of pressure with respect to V is equal to negative 1 times K times volume raised to negative 2. So which is the same as this, negative K over volume square. So when the volume is equal to 4, dP dV is equal to negative K over 4 square. And therefore, simplifying, the rate at which pressure increases with decreasing volume is equal to negative K over 16. So the units would be units of pressure per volume. So it may be pascals per cubic meter or pounds per cubic foot. So it all depends on the units here. But here in general, the units would be units of pressure per unit volume, per cubic units of volume. So for problem 2, these problems are taken from Love and Rainville, book by Love and Rainville. So suppose the container in the preceding problem is a cube with its edge E units in length. Find the rate at which the pressure P varies with varying edge length when E is 3 units. So pressure is equal to K. The volume of a cube is E cube. So we can rewrite this into K times E to the negative 3 and apply power formula. So the derivative of pressure with respect to the edge E of the cube is equal to negative 3K e to the negative 4, and simplifying, it is negative 3K over e to the positive 4. When the edge of the cube is equal to 3 units, so we have dP dE is equal to negative 3K over 3 to the 4th. So simplifying, the rate at which the pressure increases with decreasing volume or varies with varying edge length is equal to negative K over 27. And the units would be units of pressure per unit of the edge. Then for problem 3, find 2 points on the curve y equals x to the fourth minus 2x square minus x that have a common tangent line. Graph the curve and the common tangent line. So first, the expected graph of the curve would be this. It is quartic, so fourth. If it is cube, then it may look like that. Open up, then open down. If it is second degree curve, it is either open up or open down. If it is open up, if the coefficient of the highest degree term is positive. So like here, the highest degree of the curve or the degree of the curve is 4 and the coefficient is positive 1. That's why the graph begins from positive infinity, because when x approaches negative infinity to the even power is positive infinity. So that's why it looks like that. Then because it is quartic, then definitely it will look like this. There are two portions of the curve which is open up, concave up, and one concave down, then another concave up. As I said, if it is 3, then it will look like concave up, then concave down. If it is a parabola, or if it is a second degree curve, it is either open up or open down, depending on the sign of the coefficient of the highest degree curve. So because the coefficient is positive, then it begins with positive infinity from the left. When x approaches positive infinity, also y is approaching positive infinity. So more or less it looks like this. So before we find the points where the curve has a common tangent, we have to sketch the graph. Then from there, we can find the points. We can locate the points where the tangent is common. So for example, because it looks like W, more or less the points would be somewhere here. Because if we find a point here, the tangent will have no same tangent or parallel tangent to anywhere in the curve here, except for these two somewhere lowest points. But it is not exactly the same as this. It will just look like this. So we plot first -2. When x is -2, you can use your calculator, mode table. Then y is 10, or you may input -2 here, then solve this manually. So 16 minus 8, so 8 minus -2, so that's why it is 10. Then when x is, to make it accurate, -1.5, y is 2.0625. When x is -1, 1 minus 2, -1 minus -1, so 0. When x is -0.5, it is 0.0625. When x is 0, y is 0, obviously. Then when x is positive 0.5, we have -0.9375. When x is 1, y is -2. When x is 1.5, y is -0.9375. When x is 2, you just evaluate y, so y is 6. So let's plot these points and let's show it on this graph here. So this is -2, 10, -1.5, 2.0625 approximately. Then we have -1, 0, -0.5, 0.0625, then 0, 0, 0.5, -0.9375, then -1, 2, 1.5 comma negative 0.9375, then 2 comma 6, then when x approaches positive infinity, y is positive infinity. When x approaches negative infinity, y approaches positive infinity. So that's why this is the expected graph, and it appears to be like W shape. Now, if we now find points where the tangent is common, more or less, if we do the tangent line here, it may appear to have almost parallel or same tangent as this point. So we have negative 1 comma 0 and 1 comma negative 2 as our selected points. Let's find out if they have the same slope. So this is the derivative, 4x cubed minus 4x, then minus 1. When x is negative 1, so 4 times negative 1 cubed is negative 4, minus 4 times negative 1 is 0, then minus 1. So dy dx, the slope is negative 1 at negative 1 comma 0. When x is positive 1, then 4 times 1 cubed is 4, minus 4 times 1, 0, minus 1, so negative 1. So this shows that the derivative or the slope of the tangent at the point negative 1 comma 0 is negative 1, and at the point 1 comma negative 2 is also negative 1. So these are the 2 points where the tangent is common or has the same slope, same value. So the points are negative 1 comma 0 and 1 comma negative 2. And let us show the common tangent line as shown. So the slope of these tangent lines would be negative 1. So this is 0 comma negative 1, and this is negative 1 comma 0. So the slope is negative 1. This tangent will also pass through 0 comma negative 1. And this is 1 comma negative 2. That's why the slope is negative 1. So that's it for this video. I hope that you were able to understand the explanations and the solution presented.